Large language models are transforming how we solve complex problems, from math and coding to scientific reasoning. But behind their impressive answers lies a critical question. Do they actually follow our instructions while they're thinking? Most research focuses on whether the final answer is correct. But here's the problem. Even if the answer is right, the model may have taken a dangerous shortcut during its internal reasoning. And that's exactly what we set out to investigate. We introduce ReasonIF, a new benchmark designed to measure how well large reasoning models, or LRMs, follow user instructions during their reasoning process. Not just at the end. Throughout. Why does this matter? Because a model that ignores formatting rules, uses forbidden languages, or violates length constraints while thinking, even if it gives the right answer, is unpredictable, hard to audit, and potentially risky. Imagine a financial analyst using an LRM to generate a report. The user says, use only English, stay under 80 words, and add a disclaimer at the end. The model delivers a correct answer, but the reasoning trace is in French, 200 words long, and ends with no warning. The final output looks fine, but the process is compromised. This isn't hypothetical. In our study across 6 leading open-source LRMs, including GPT-OSS, QN3, and DeepSeek R1, we found that the highest reasoning instruction following score was below 0.25. That means fewer than 25% of reasoning traces actually follow the given instructions. Even more concerning, the harder the problem, the worse the model gets at following instructions. When we tested models on challenging datasets like AIME and GPQA, their ReasonIF dropped significantly compared to easier ones like GSM-8K. But here's what's truly alarming. The model's main response often appears compliant, while its reasoning trace does not. We compared 2 metrics, ReasonIF, instruction adherence in the final answer, and ReasonIF, instruction adherence in the internal steps. Across all models, ReasonIF was dramatically lower, averaging just 15.6%, compared to 57.3% for ResponseIF. Take QN3-235B, which scored 78.7% on ResponseIF. Its ReasonIF, only 25%. So it looks like it followed instructions, but in reality, it ignored them during the thinking phase. This disconnect raises serious concerns. Models that don't follow instructions during reasoning are harder to debug. They're more vulnerable to reward hacking, where the model learns to fake correctness by skipping steps. And they become less transparent, making it impossible to verify whether the logic is sound. So why does this happen? Our analysis suggests it's not due to poor prompt design. We tested multiple prompt variations, including explicitly defining the reasoning trace with special tokens like thinking and thinking. The results were nearly identical, meaning the model isn't responding to wording. It's failing to internalize the instruction at all. We then explored 2 potential solutions. First, multi-turn reasoning. We let the model reflect on its own output. If it violated an instruction, we gave it feedback. Your reasoning didn't follow the word limit. Then we asked it to try again. The result? ReasonIF increased by 16.6% on average. For some models like DeepSeek R1, the improvement was over 23%. But even with this feedback loop, the success rate never exceeded 45%. And accuracy improved too, suggesting that seeing its own mistakes helps the model learn. But multi-turn reasoning adds cost and complexity. It's not a scalable fix. So we tried something more direct, reasoning instruction fine-tuning, or RIF. We trained GPT-OSS-20B on synthetic data where the reasoning traces were carefully rewritten to follow instructions, like switching to uppercase, removing commas, or formatting as JSON. The results were striking. RIF boosted the model's reasoning ifs from 0.11 to 0.27, a 154% improvement. Accuracy stayed nearly the same, dropping only slightly from 0.77 to 0.73. This proves that instruction compliance during reasoning can be learned, but it requires targeted training. However, we also found a trade-off. When we fine-tuned on more data, especially for the word limit instruction, the model overfit. Accuracy dropped to 0.68. So while RIF works, it's not a silver bullet, and we must be careful not to sacrifice generalization for specificity. So what's the takeaway? Large reasoning models are powerful, but they're not trustworthy by default. Their ability to follow instructions during reasoning is weak, inconsistent, and gets worse on harder problems. This gap between appearance and reality undermines transparency, safety, and reliability. We're not just asking models to give correct answers. We're asking them to think the way we want them to. And until we build models that follow instructions throughout the entire reasoning process, not just at the end, we can't fully trust them in high-stakes applications. This is why ReasonIF matters. It's not just a benchmark. It's a wake-up call. We made our dataset and code publicly available at github.com/ik104007/ReasonIF. Because if we want AI to be truly controllable, interpretable, and safe, we need to measure it where it counts, in the thinking, not just the answer. Because the future of AI isn't just about smart models. It's about aligned models. And that starts with making sure they follow instructions every step of the way.